Okay, we're ready to start. You want to come?
So, hello. My topic is 3D multi-resolution mapping of the recurring slope linear features at the Valles Marineris. So I'm Yu Tao from Mula Space Science Laboratory, the imaging group. Peter Muller and Kiki Putri also contributed to this talk. So recurring slope linears are these meters to decameters white dark stripes found on the steep slopes. Oh, sorry, I wanted to use the arrow, okay. So can you see this? Yes. So this is I think it's either this. Thanks. So these meters, decameters, dark stripes found on the steep slopes, which grow during the warmest time of the year and fade during the cooler time periods and reappear again the following year, but not exactly necessary in the same place. So the highest concentration of RSLs are found in Valles Marineris. So my research aims to study these RSL features across the whole of Valles Marineris. So it's showing in this map there. So this work contains 3 parts of this work. So the first part is 3D reconstruction, and second one is super resolution restoration, and also the last part is automatic tracking of these RSL features. So we use the HRSC, CTX, and HRSC data for this work. So the first part is the 3D reconstruction. So previously we have developed this multi-resolution automated DTM processing chain called the COSCO, which stands for co-registered and stereo pipeline with gotcha and optimizations. It's based on this type point-based multi-resolution image co-registration and depth score correlation and region growth with subpixel refinement method. It has several features. Firstly, it's co-registered with the HRC and MULA data. And secondly, it has improved the DTM completeness, as you can see from some test results for the MSR and the MER landing site stereo pairs. And also, we work on reducing the DTM artifacts, and also aiming to improve the DTM accuracy by refining the matches. So we also have uncertainty value for interpolated area. So the COSCO system was applied to generate about 5,000 Emerald CTX 3D imaging products covering 19% of the Martian surface in the previous project. So it also can be applied to HRC, and Cavus is under experiment. So there's some results from the first part of the work include hundreds of CTX DTMs and also some of these HRC level 2 DTMs. So we mosaic them together to create a full mosaic for the Valles Marineris area. And you can see from the bottom right of this figure there, the green one is the already processed CTX data. And we are on the way to complete the rest of them, which is showing the blue color in the last figure. So after this been done, we're going to create a full mosaic from CTX for this Valles Marineris area. So the next part of this work is super resolution restoration. So this comes from previous Earth observation project. We developed this Megigan supervised system based on multi-angle feature restoration and deep supervised networks to produce 3 to 5 times resolution enhancement with given repeat low resolution input images. So the Megigan supervised can combine the image information from repeat observations from various viewing angles, which you can see from the example of the high-res image on the top left figure, and the comparison of the supervised image for two zoom-in area. So This system has 5 steps, including segmentations and shadow labeling, initial feature matching, subpixel refinement, and feature densification, as well as estimation of the image degradation models, and also the generative adversarial network training and supervised refinement as the last step. So more specifically, there are several algorithms including subpixel matching and the region growing and image degradation modeling and the GAN deep learning network. Most of them have been published, so if you're interested, can talk to me after this. So the last part, after we get the 3D information and the supervised image, so the last part, okay, so the last part is the up to just 2 more slides. So is to automatically track these RSL features. So due to the static nature of the supervised technique, we're able to restore the matched and features, which is unchanged, and meanwhile automatically track the unmatched pixels to characterize the bizarre and measure change. So there's examples showing the high-res image on the first figure and the automatically masked RSL features on the second one, and combining with the 3D information. So able to derive a lot of information from this. So last slide. Yeah. So we plan to apply this supervised and DTM system to all our cell sites, which is showing on this figure there. We repeat high-res images available and allowing a statistical approach, testing different models with RSL formation. So as example, this Paris month, which is one of this area. We have some initial feature RSL tracking results showing on the bottom right figure. This is 31. This is 3 Martian years from Martian year 31 to 33. So we plan to create the first regional map of RSL currents for the Valles Marineris with started growth rates, timings, and topographic information in the next stage of this project. Thank you very much. Both of this processing is pretty heavy because we have some algorithms. Currently, the algorithms are being optimized. It's being ported to GPU by other GPU developers in our group. So hopefully it can be faster later on, but currently we are about it depends on how many repeat image, how large the image is. So it's several hours to 12 hours like that for one scene. So no, not too bad. Sorry? Oh, yes, right. The CTX data is currently gradually, batch by batch, being released with the ESEC gas storage facility. And the software is being released through the NASA Ames GitHub. The COSCO software is being released. Yes, we have under collaboration on this. But the supervised system, because there are a lot of commercial projects is using that, so we haven't have a plan to release at the moment. But maybe. Right. Yeah.
Good afternoon, everybody. I just want to share some experience that with TOPCAT, which is a software. I'm not paid for that. I'm just a simple user who love this software because it's very powerful, in fact. And I would like to insist that since it was made for astronomer, but in fact, we can use it for planetary science, and it's very powerful for planetary science data, especially coming from imaging spectrometer or camera. So TOPCAT is a tool for operation and on catalog and table. So it's a manager of table. We can say that. I'm not the developer. It's Mark Taylor, which is based on England. It's a powerful VO tool, so it means that I will not develop that, but we can discuss about that later. It's linked with the other tool of the VO. So basically, you can send data when you do a query on Vespa, for example. You can send the data on TOPCAT. When you are on TOPCAT with your own data, you can send the data to another tool, for example, on Aladdin. So it's very flexible in that way. And you can also, into TOPCAT, make query to distant database to download the data of many data sets. It's a very light software, so basically it's 30 mega. You just have to download the app, and to launch the app, it's very simple. It's very fast. I mean, you can calculate, you can compute, you can map some million of data, million row tables in some minutes, in some seconds, depending of your computer. But you don't need a huge server or a huge computer to do that. And it's very multifunctional in the sense that you can do, you have a lot of tools inside TOPCAT to do some statistics, to do some figure, to do some mapping, some things like that. And also you can edit your table, etc. So it's this figure basically. This is the main interface of TOPCAT. So it's very simple. You will load your table with this icon. You will save your table or your session if you have many tables, many subsets inside. With this icon, then you can browse your table. You can define a subset. You can do histogram, figure, projection, cross matching, etc., etc. So the idea is to use TOPCAT inside a workflow with the remote sensing data. So basically, you have your data. This can be just the raw data acquired by the spacecraft. You have the derived product of that. You have the geometry. You have the derived product. You can also compute your own interesting data, derived data. So this is the part of the processing. So you can do that with Python, with IDL, what you want. The goal is to prepare a table with every interesting thing that you want. So you can have a column with a label to identify which pixel it is. For example, the idea also is to use one line is 1 pixel of your data, for example. So you can have a label, you can have a spectral slope, for example. You can have a reflectance, you can have a latitude, a longitude, etc. in a column, and this for every pixel. So you have your table, and then you will ingest that into TOPCAT. And if you use, for example, FITS format in binary format, it will just take a few seconds to load the table, even if you have a 1,000,000 row table. So it's very fast. It's a table manager in the sense that it's compatible with many formats. I said that you can use the FITS, but you can use the VO table, you can use ASCII table, you can use CDF, etc., etc. You can edit the table. So of course, if you want to modify a value inside, you can do that. You can do subsets, and I mean you can do that by many different ways. If you want to define a subset, so by subset I just want to say that it's a part of your data, of your table, in fact. It could be based on an equation, for example. You can do that because you have also a mathematical library. So if you want to sort the data between two values or something like that. But you can do that also based on a map, based on a graphic. So you can draw a subset of data. Okay. There is a lot of data analysis tool, statistic histogram, automatic action, and very rich graphics tools. And you can do also mapping. I will just show you some kind of figure that you can do. So you can do simple histogram, density plot, 3D projection. So for example, here it's a map of Ceres, of the topography of Ceres, made with 1 million of points. Here it's a map. So you have two kinds of map made with single point for 1 pixel. In that case, it's good if you have a huge data set. In that case, more than 7 million points. And it's just done in a few seconds. And there is a new tool which is very useful. In fact, you can project the real footprint of the pixel, of each pixel, in a projection. And in that case, it's better for more local study. And that's it. I will end at this point. So it's free, and if you want more detail, you can go on this address, or you can speak with me after for the poster, and I can do live demo. You will see it's very fast.
How much time does it take you to plot like the complete footprint of an image?
To
plot the footprint of the image.
Alors, it takes a bit more time than this map, for example, because here you will have to represent 7 million points, for example. In that case, if you want to do the same but with the footprint, which does not make sense in that case because you will see no difference, it will take more time because you will have to manage, for example, about 28 million, 30 million points. But it's still manageable. I mean, you can do that in maybe not a few seconds, but 1 minute, 2 minutes. So, so yes, you can just take a break and it's done.
But these points are stored as single points?
Yes, in fact, the philosophy, if we can say that, the idea is to have a table in which one row represents 1 pixel. In fact, at the beginning, the data are here, and they are stored in cube, hyperspectral cube. And in fact, you will take each pixel by each pixel to make a table, and you will compute your parameter.
So in that case, you have 7 million rows?
Yes, in the table. And it's stored as binary table, so it's not so heavy. And it's loaded in TOPCAT, like you just click and it's already in the table. If you do that with the ASCII format, it's a bit more time because the software has to read the line, each line after each line. So.
The polygons, these are the data and the footprints, or are
yes.
Okay, so we have the value of the data and the polygon.
Yes, in fact, if you.
The polygon is all stripes, or is every polygon every pixel?
Alors, I'm not sure to understand everything, but I will explain the process. In fact, in that case, it's a new function. You just have to define a new column, which is also possible, which define an array based on the longitude, latitude of the corner of the pixel. And then you have a new function in the projection tool where you can say, I want to plot this array, and you will represent the footprints. And what is possible to do is to just have the footprint, which is without any data overlap. And you can, for example, here it's maybe the radius. So in that case, you will fill each footprint by the value of the same row, and you have the data. What I didn't say is that you have an active support of Mark Taylor, the developer. So basically, if you have a query, if you have a question, you can contact him and he will answer in the day. So it's very nice.
Next one is Pierre-Antoine.
Est-ce qu'il y a moyen de voir les notes en même temps, sans que ça apparaisse ici? C'est tendu. Est-ce que du coup, faut arrêter maintenant? C'est bon, c'est pas grave.
Non, parce que je vais
essayer de me souvenir du coup.
Dans la première phase.
Ouais, mais ça va, ça.
C'est plus important.
C'est pas grave, c'est pas grave. Désolé. Ah, c'est pas grave. So, hi everyone. My name is Pierre-Antoine Tesson. I'm a PhD student of Daniel Mej here. So we are all in this group located in Wrocław in Poland. And today I'm going to make a very short presentation about the work I did close to in the Valles Marineris region. This work consisted of tectonic mapping of this little area here, which is called Hydrae Cavus. And the reason for this work, it was to find new evidences of strike slip deformation in the vicinity of Valles Marineris. And I decided to focus this presentation more into like methods and data sets. And then if you want to discuss the results and the science, I have the poster right here. So to do this, I've used different data sets. As a base map, I've used the CTX mosaic from the Murray lab, which you can find an abstract from LPSC describing this data set. And I also use individual images combined to that. There is a reason for this that I will explain later. I also used Themis-derived thermolination to distinguish different terrains. And for topography, I've wanted to use first an HRSC DTM of Valles Marineris, which is roughly 100 meters per pixel. And quickly I realized that it would be very difficult to work with this DTM because you can see here on this little plot, you have the topography derived from this HRSC DTM here in red compared to the MOLA topography. They are voluntarily shifted by 800 meters. And you can see that these different bumps and slopes, they don't correspond to any feature on the surface. So this DTM has actually a lot of artifacts. So in the end, I was like left to use this basic MOLA DTM of 463 meters, which for tectonic mapping is really not great. In the future, I intend to use to create some DTM based on CTX using AIM stereo pipeline. And the difficulty with this area is that there is really almost no high rise, no Crescent or no Cassis, at least yet. The reason for this is that Valles Marineris is a very busy area. So what do you see here is actually a screenshot of CAST, which is Cassis Suggestion Targeting Platform. I don't know if you are familiar maybe with HiWish. It's exactly the equivalent of HiWish. It's a platform, if you have any suggestion for Cassis images, then you can write a nice suggestion and it will be given a priority, and depending on that, maybe it will be taken or not. And what you have in pink/purple is Cassis suggestion, and in yellow are high-rise suggestion. And the area we are interested in is just located here in the north. And you can see that there are a lot of suggestions, especially in Coprates Casma. So when the spacecraft is flying over this area, so either like TGO or MRO, it's flying over there, and then when the targeting specialist is choosing the target, like most often they choose like a target in this area, which means here you have to be really patient if you want to obtain your data. Another comment I wanted to make, I said at the beginning I use mostly Miralab CTX mosaic as a base map, but it turns out that to do geological mapping, it could be sometimes a bit misleading. You can see here in this example, when you look at the image, so this is extracted from this mosaic, that you have the feeling that there could be maybe geological contact here with different albedo. But if you look at the actual CTX image, this appears less clear. And then I think Miralab mosaic is a very great data set. And it's good for if you're doing crater counting or anything. But to do geological mapping, I think it could be sometimes misleading. So I would recommend to be careful. The reason for this is the way they did the mosaic. Here you have a figure taken from the abstract they published in LPSC. And you see that to construct the mosaic, they have taken different CTX images, but the seams are really not straight. They have actually curved like this. So when you have here at the boundary of two images, this is exactly what you see here. So this can appear as a fake geological contact. But in the end, even with relatively little data, I managed to do a very preliminary map. Just few interesting results. I managed to find some evidences of dexterous flagship deformation in the basin. And there is also a very interesting relationship between the tectonic features and the different lava flows, which are early Hesperian lava flows there. But I would be very happy to discuss more in detail at the poster. And that's all I have to say. So.
I don't understand your offsets from the molar to the HRSC.
The offset is actually the offset it was there already, but just for this plot I didn't correct it. Actually, I think it's the problem is the difference of reference elevation. But just for this plot, actually, I left it because then you can compare just the problem is not here. It's not the offsets. The problem is here you have the feeling that you see like some topographic features, but actually they are just artifacts, and just wanted to point them out. Of course, like even if you will have like features at this resolution, maybe they're not visible at molar resolution. But it was just to say that this HRSC was, at least in this area, was not cannot be used. So at least for tectonic mapping.
How do you prove that it's artifacts?
Well, really, when you look, actually, it's not very convincing, but I agree. But when you look at the CTX image, and really, there is absolutely no reason sometimes like to have like a big hole or a big ridge, and you see that the surface, of course, it's just from the CTX image, but you see it's rather flat. So.
Remember the orbit number?
Sorry.
Remember the orbit number?
It's for the HRSC DTM, you mean? It's a mosaic, actually. It's a mosaic. So I will need to look for this this number specifically, but I can check if you want. Yes.
The questions?
Thank you.
Next one is
Okay. Maybe. Can I use this as a pointer or as a switch style? Maybe let's use the keyboard. Oops. Okay. Okay. I have to speak in English. Hello, I'm Sebastian. I'm in the HRSC team, and I take care of a map server dedicated to HRSC, so where you can download the products and It's really custom tailored for HRSC. And the idea was that all this pre-existing infrastructure for the HRSC map server is an ideal case for connecting these virtual observatory infrastructure to these existing services. So here's an image of the server. You can download the data, preview the data, browse the footprints, and the data you can download here is really ready-made for Arcgis, so you don't get offsets when you download the correct data, and so you don't need to take care of the data processing yourself. Yeah, it's really made for HRSC and can handle several projections, even polar projections, and you can preview the data in the web interface, and you can also visualize it as time series. So for the poles, for example, when you have the surface changes related to the ice or spiders or stuff or albedo features, you can visualize them in the system. You're happy to approach me, then I can show it to you. It's out of the scope of this presentation. But I want to focus on the additions we made to the server. So this is all the pre-existing infrastructure, the gray box, the gray big dash box here. And we only added this part. It's the EPN TAP services provider. And then this whole system opens up to the Vespa infrastructure. So it's actually a small piece of additions, which are quite complicated because I'm totally out of the astronomy topics. So it was quite a hard learning curve for me to get all this metadata right. And I think it's still a lot of things to do there in general to connect the GIS stuff with the astronomy pieces. And this is, let's say, the result. So you can really display the data now in, these are footprints, but you can query the footprints and check for overlays for other available data. This is MISAR. It's one of the VO tools. Here you have just seen TOPCAT. You can also use that for displaying the footprints and the HRSC data. So that's it. And this is now an additional thing. We also wanted to make the service easily available in QGIS. So you can just paste this piece of code, piece of URL into the WCS connection window of QGIS, and you can browse all the available HRSC. In this case, these are DTMs, but we also have the nadir images. And on my poster, you can see the piece of code which is necessary to produce such a thing in map server. Map server is the software we used for that. And yeah, so in theory, it's now ready, and you can show nice pictures with these footprints overlaying on top of each other. But we are handling highly resolved data here, and even if the footprints look nice, if you go down to pixel scale, you will see that they don't match very often at all, because actually when you look in the Vespa tables, you see CRISM services and HRSC services, and they use different reference systems. So when you overlay them, you get quite crappy results. Actually, you can't use them. So there are some unresolved issues with regards to these services. So currently, it's solved that there are special fields in this EPN TAP table called spatial coordinate description in the case of CRISM. So that's not even the same. So. And we used map projection because I've been told that this is maybe wrong. So it's really ongoing what we are doing here. And this is an example for a projection code in the proj notation. So if we leave it like that, it would be the responsibility of the client to take care about these unconformities. But of course, we could also solve the problem by standardizing all our data. So that would mean reprocessing half of the data or all of the data, which is also not a very nice option because we want to avoid it. And then there are issues about even missing descriptions of coordinate system parameters, like if it's planetocentric or planetographic oriented projections. So we also have to document these. And then at the end, even if you do everything correct, you will still have offsets because the pointing data is not good enough to overlay CRISM on HRSC. You always have to, so if you're working on a GIS without even VESPA, touching VESPA, you have to shift the data or rubber sheet the data. So that could be solved by either block adjustments, what we are doing in HRSC. So we try to produce a very correct data set as a reference for Mars. But you would have to do that with all the other instruments as well. And or you can do co-registration, goes into the direction of what Utah just reported about. That's it. Thank you.
Do you have any idea why you have these misadjustments? So do you think this is due to, so when you use different prism HRSC, for example, when you go to the pixel value, you still find something like misplacement. So you have an idea why?
Sure. I mean, this registration things, they're coming from the SPICE kernels. In HRSC, we do like bundle block adjustment and things to correct for these SPICE kernels, and then there are reconstructed kernels or at least reconstructed external orientation for the camera. But for CRISM, you don't have such things. So it's because it's a photogrammetric instrument, and you can do these things in the stereo domain. So there will always be these. I mean, it's much better than, for example, sensors on Earth. On Earth, they are much more worse, but there you have control points on the ground, and that's why they have these highly precise kernels for space missions. But it will never be as perfect as a pixel scale. I hope that it's not like this, but
maybe a unified pipeline processing of both HRSC is may solve this issue.
The idea would be that you have a reference data set, like it's now Molar, but maybe HRSC will get into this role because it's like 50 meters resolution and it has a very highly controlled network on the ground. So you really have to, even if there are artifacts, for example, but you really know where this pixel exactly is because it's a photogrammetric instrument. You can do that bundle block adjustment. And then you would have to co-register other instruments on top of this existing reference data set. That's what they are planning to do with ISIS, for example. So if, for example, CASP-GO goes into ISIS, you can do that. Or I think ISIS people do have techniques for this by themselves. Or for example, the ASP has stuff like, or wants to do stuff like that.
In terms of the attitude errors, I suppose we're using the attitude kernels for the planetary.
No, it's reconstructed. I mean, you can even download the CRISM data from the team side, and it's not perfect. It gets even worse with high-rise data. If you just download the official high-rise data and you put it in Arcgis, it's off by a couple of 100 meters.
We used to recommend to the teams to use the plan because the measure ones that gets, and we were thinking, we had to do the dynamics that they are noisy and not very accurate. But recent point investigation showed that the measure attitudes are indeed much better and very good. So I'm not completely sure that the teams really have used them before. They are only available relatively recently, and I would recommend to give it a real check what you are using, the planned ones or the measured ones. And if you're using the planned ones, try the measured attitudes. Maybe. But
with measured, you're talking about the reconstructed.
No, we don't have to construct it. Measured means from the sunset, or from the star track. Measured means just measured by the star track.
But you're talking about which camera now?
This is a spacecraft.
But for MRO or? Yeah, no, Mars Express is perfectly good. The problem is MRO and CRISM. and HRSC and CTX. They're all shifted. And in a way that you can't predict the shift. And for Dawn, for example, they have the same problem. Dawn framing camera, they are off by 500 meters in the very new cycle. Yes, you cannot use that accuracy for pixel alignment. That's just not the scope of this. I mean,
last question.
Out of curiosity, do you think that providing the projection parameters would allow you to reproject the data on the cloud?
No, I don't think. As long as it's like projection parameters, yes, but you shouldn't change. There shouldn't be a difference in the ellipsoid, for example. Here you see the mass radius for.
Can you change the projection?
It's very buggy. I think in QGIS it's too buggy. I guess it's too buggy.
Maybe Stefan was referring to this GSM, CSM camera sensor model, which is being implemented. So it could be something that it's a camera model which can be plugged to the hooks. So, for example, also in GDOM, if you want. So it is a new implementation which USGS is working on, and it would be like not easier than the existing implementation like ISIS, but simply the touches the camera model out of ISIS can be plugged in GDOM.
But we are talking about block adjusted level 4 data. So camera model would make sense for level 2 data, but this HRSC data is bundle block adjusted level 4. So you cannot get better with any other camera model. They invest like years of photogrammetric experience into getting really the right pixel location out of every pixel.
So you just need block adjustment, bundle adjustment.
They do block adjustment and bundle adjustment. So.
Sorry, you and Gloria.
I said plan map.
Go to the next slide.
No,
Pointer.
sì. Okay. Okay. So I will introduce you what we are doing in order to produce a characterization of Tsiolkovskiy crater as a possible landing site. So the data we are using is the Lunar Reconnaissance Orbiter camera WAC. Okay, we collected the mosaic, and it has a resolution of up to 100 meters per pixel. Then we are using the DEM merge obtained by Lola and Kaguya with an horizontal resolution of 59 meters per pixel and a vertical resolution of 34 meters. And finally, the Clementine color ratio with a lower resolution of 200 meters per pixel and obtained by the following color ratios. Tsiolkovskiy crater, it's a crater of 180 kilometers of diameter. It is located on the far side and before on the island Felpatic Island Arena. It is formed by an oblique impact coming from northwest-southwest direction. And it is considered one of the best examples of far-side mare volcanism, since it has this dark mare bottom. It is also characterized by this well-preserved and very bright central peak, in which has been defined the presence of pan, which is poorest anarthosite, and olivine. The olivine also along the rim. Okay, and it is also characterized by an crater floor elevation difference of about 450 meters from the northwest quadrangle, which is the higher elevation, to forward the southeast quadrangle, where there is the lowest elevation. Okay, this is the morphological mapping we have been producing now, just with the linear features. Okay, in this slide you can see some details. For example, here you can see that there is the central peak, which is clearly discernible with respect to the smooth floor and from the hummocky terrain. And here we can see the steep slopes, steep scarps that are present in the rim. And here, always in the rim, we can see some smooth ponds, like this one, and a steep scarp. Okay, remember this screenshot for you. Okay, this is the complete morphological mapping with the units, where we distinguish some crater floor units for the smooth and hummocky floor and the discernible central peak, and crater wall units for the smooth ponds, the steep scarps, and the rim, obviously. Okay, this is the spectral mapping that has been produced on the Clementine color ratio. And you can see that there are a lot of approximate contacts since the resolution is very low. You can distinguish also this megapixel that don't help the mapping. Okay, again, the screenshot of before, you can see that the central peak is distinguishable from the yellow-orange smooth floor and from the hummocky terrain. The steep slopes, the steep scarp has this bluish color, which is discernible from the crater rim, which is red. And again, the smooth ponds are red, so are not discernible from the crater rim. And again, the steep scarp. Okay, so in the future, we will conclude the spectral mapping by producing also the polygons. And we will produce an higher resolution geological mapping by means of lunar reconnaissance orbiter NAC and Kaguya terrain camera images. And then all the possible analysis in order to characterize the site for a possible lander. That's all, thank you.
Fancy animation? No, just very simple animation. Okay, good afternoon. I'm here to present the new version of MATISSE that is already online for a beta version. The link I will be showing it at the end of the presentation. MATISSE is online from 2013, 6 years ago. This was the first demo version of the tool. And during these years, has been upgraded deeply. We started with Comet 67P with Virtis Rosetta. Then we ingested the VIR data from Dawn. We added the connections to Planet Server for Mars with Vespa for Virtis Vex, and so on. We also use MATISSE in several educational and outreach programs successfully. Students have been highly engaged and used MATISSE easily. What's happening? Okay. This is not working well, but I will speak. Okay, now it's time to rethink MATISSE, and we have a new version totally from scratch. Okay, don't look at the animation. We have a PostGIS DBMS to correctly ingest geographic data. We have a very user-friendly interface. We're using also planetary feeds in order to exploit JS9 potential. And so also the 2D image is interactive, and we continue to use the VTP for 3D visualizations online. This version of MATISSE will be also usable from script. Okay, this works, I don't know why. Okay, this version of MATISSE is also usable with servlet, so you can write your own scripts to connect without a web browser. And we are thinking of adding HPC and artificial intelligence to the tool, so we can better exploit data within the tool. We thought MATISSE as a hub for scientists, but also for citizens. For science, we will add Juno GRAM data, CASIS for Mars. We will continue to use VESPA connections, and we hope to support also PlanMap. But we are also open to educational, for example, by using virtual reality applications and other student programs. So this is the link to the beta version of MATISSE. Has very limited functionalities for this moment. It allows the use of VIRDON data from VESTA. And we hope you could start to use the tool and give us feedbacks about it. Thank you, and I'll wait you for at the post. Okay, in the old MATISSE we have Virtis Rosetta data, VIRDON, Virtis Rosetta, VIRDON, both for Ciris and VESTA, CRISM by using Planet Server, VirtisVex by using VESPA, this one. Okay. Okay.
So we'll talk about the mineralogical mapping of airless bodies of a solar system, and in particular, I want to show you 3 examples. The spectral properties and the mineralogy of a surface can be derived from spectrometers or multi-filter cameras.
They are different instruments and cover also different spectral range. Generally, spectrometer, or in this case, imaging spectrometer, can arrive up to 5 micron, and the multi-filter camera arrive at 1 micron, and they have different number of spectral channels, hundreds for spectrometer and 10, 12 for cameras. These are okay. These are the steps to process the data and to arrive to a product useful for the analysis. We have two common steps, so calibration and artifact removal, but after we have to change a bit the procedure. So in the case of the spectrometer, we have to remove the thermal emission in the infrared part of the spectrum, apply photometric correction, select the spectral indices, and project and produce global mosaics. For the cameras, we apply photometric correction. After we project the data, we co-register the different filters, and we produce the global mosaics, and after we can choose and calculate the spectral indices. The spectral parameters depend on the surface and so on the spectrum. I show you 3 examples: Mercury, Ceres, and the Moon. The first one is a typical spectrum of Mercury from the multi-filter camera on board messenger. Here we have 8 points in this spectrum in the visible range. And you see that the spectral characteristics for Mercury are very different from the other. So we have to choose spectral parameters studying the spectrum. For Ceres, we have several absorption bands, and for the Moon, we have the typical band of the pyroxenes at 1 and 2 microns. So this is, for example, the results of a map, an RGB color composite map for Mercury. And here we have the 3 principal spectral slopes. The global slope that indicate the different terrain maturity, the infrared spectral slope that can indicate a possible absorption around 1 micron, and the spectral slope close to the UV range that can indicate the presence of opaque material. And so in this map you can see the variation of these 3 slopes. For Ceres, this is the global map of the 3 principal absorption bands. We have in red the band depth at 4 micron for the carbonates, the band depth at 2.7 micron for the magnesium phyllosilicates, and the 3.1 micron band for the ammoniated phyllosilicates. And also here it's possible to see the variation of these mineralogical phases in red here, the carbonates areas, and also in blue-violet, the ammoniated phyllosilicates, and so on. And the last example is the Moon. This is in particular the Apollo region, and these are the data from M-Cube on board Chandrayaan-1. And this is just an example of 2 different spectral parameters, the band center of the pyroxene at 1 micron, and the band depth. And so in these smooth planes inside the crater floor of Apollo, there is a spectral variation. So this approach is useful to analyze the composition, but it can also be merged with a stratigraphic map, morphostratigraphic map, and so it's possible to derive units that can put in relation geology and also composition. So if you need other questions or you want some clarification, I have the poster there. Thank you.
I'm geologist, petrologist, so I have a specific question. What do you mean by opaque materials or opaque minerals? Sulfides, oxides, or both, or some very specific?
No, really, for mercury, we don't have a specific opaque material. It's just an indication. We cannot see what is the opaque in this case.
But for the moon, you also distinguish this, right?
Yes, for the moon, yes, you can have a.
It's not that each of these minerals is slightly different feature that, for example, you gave this specific range
for mercury?
Yes, here on.
Yeah. So we have the data in this range. So it's not UV, but it's close to the UV range, and we can just observe here just the variation in this range. So, but it's not easy for mercury to define the process. Yeah. Yes, for example, we have also blue slope for fresh material, for example, not only for opaque material, but we have to use, for example, reflectance to distinguish if it's opaque or not. So mercury is a particular case, and we can see if we have some spectral variation and combining different spectral parameters, but we cannot see what is the specific. Yeah.
I think we can discuss like more.
Yeah.
Thanks a lot.
Thank you.
More questions? No. So you're good. Take your times to discuss the posters.
You're very much on time.
Yeah.